types are. So for example, if you know uh, in short, Boolean, char, bit of pointers, I guess. So all of the information that was covered in the Lecture Zero booklet that was given to you, I suppose that should be enough. And yeah, so assuming that you've read it, and I'm hoping that you have, uh, the next few slides should actually be very easy. But let's go with them step by step, right? So the first question that comes is, uh, why do we need data structures? Well, to be honest, I mean, if you want to represent anything like any problem, so for example, how does uh, let's have a look at Google Maps, for example. So how does Google Maps try to give you directions? So I'm pretty sure it is creating some sort of a map, right? Uh, how do you solve a system of simultaneous linear equations or anything? But in anything that you do, computers essentially need some sort of variables and some functions that will get computed. So all of these will be represented in some sort of structures that hold data. And these can be very simple. For example, your int data type is in a way a very, very trivial data structure. It is storing some number, that's all. But even that is a very trivial data structure in a way. Your array, it's a bit more complicated. And it actually is a type of data structure that we'll be discussing today. So, uh, spoiler alert, it's called linked list. But yeah, let's get to it. So, let's get to some essentials and some recap of what you expected to know to make the most out of this. So I I'm pretty sure a lot of you or most of you have watched the movie Inception. You know, it's like a dream within a dream within a dream within a dream. And it's kind of like recursion in real life, but okay, not real life. I mean, if Inception was a real life, then it would be pretty crazy. Agreed. But then there's this one thing, specifically with which this picture is made in mind. It's called the Drost effect, in which you have picture within a picture within a picture within a picture, and it's the same picture repeating. So, in a sense, this is the spirit of recursion. Like, uh, formally, you would say that it is something like a function which calls itself. Sure, that's a bit of a boring way of doing things, but the idea is that you do an operation which again calls that operation which again calls that operation. So, do you remember the time when we were kids and we used to have the three wishes of the genie, and everyone knew that the first wish should have been to ask for three more wishes. So from childhood we were actually doing recursion, because you get the three wishes, the first one asks for three more, and the first of that asks for three more, and so on and so forth. So that's recursion, uh, in the fun way. But let's have a look uh, and how you would do it in code, for example. And this is an example that I'm pretty sure, once again, everyone has seen or used within their life. I'm pretty sure a lot of you have guessed it, but here it is. So yeah. So remember how we were told that we have to take, HCF, and there used to be like complicated methods of doing it. So for example, you could uh, find out the factors of both numbers and then see, okay, these are the number of times these factors come in common. So let's say you do prime factorization, and then you say, okay, these prime factors are common these many times, you multiply it, and that's HCF. It's a very boring and a very unintuitive and, okay, very intuitive, but not a very good way of doing things, right? You cannot generalize it to any number. In fact, sometimes you can't even do prime factorization. So, uh, yeah, that's a problem. Is there a smarter way to think about it, though? That's what Euclid was thinking. So let's have a look at this. So for example, you want to take the prime factor of 106 and 16. Is the prime factor of 106 and 16, is the HCF of prime of 106 and 16, but won't it be the same if I subtract 16 from 106? It should be the same, right? Because if 106 is 16x plus something, then and if the only thing we're concerned about is the remainder, then you can just reduce 16. So the HCF of 106 and 16 should be the same as HCF of 90 and 16, should be the same as HCF of 74 and 16, and so on and so forth. But if you remove it 6 times, and if you remove 16 6 times, you get it to be the same as HCF of 10 and 16, which is the next step. And then if you remove 10 from one side, it's the same as HCF of 10 and 6. And if you remove 6 from it, it's HCF of 6 and 4. And then so on and so forth. So what essentially are you doing? So you're taking a big number, then you're taking a small number, and you're finding the remainder of the big number when it is divided by the small number, and you're making that the small number, and you're making the older smaller number as the new larger number, and then you keep repeating this again and again and again, right? So this one logic, which you can see in this function, this one logic keeps repeating, right? So the GCD of here in this function, if you see, so the GCD of 106 and 16, assume that let's say x is bigger, let's say y is bigger, sorry, will be the same as GCD of what is 106 mod 16, which is 10 and 16, and then it goes back here, and then you keep going on until the smaller number, which is the remainder term, is 0, which is what exactly we were doing. So now this is the beauty of recursion. You don't need to write a complicated formula. You don't need to write a complicated long loop. You can just do it in very short lines of code. You could have also written this using a while loop with a while true and a while true loop says that it terminates when this condition happens, but then that's a longer code basically. So sometimes recursion is very pretty. As you go along in your degrees also, you'll see that a lot of engineering formulas are also solved in a recursive way. So for example, you will have a formula which is yn equal to something plus yn minus 1. So recursion does become a very important concept in all of your engineering, really. And now this algorithm, think about it, it was some thousands of years ago. So people were really smart. I mean, even we've done recursion as kids, as I said earlier. So that's recursion in brief as a concept for you. Code implementation, there's no standard code implementation for it. And you can implement it in any way. Just the crux should be implemented so that a function should call itself. Now it can be more complicated. For example, you can have a function that is calling another function that is calling the same function back again. So now that is a bigger type of a loop, but it's still recursion in a way. So function A calls function B, B calls A, and so on and so forth. So that is also valid. The choice of how you want to implement recursion stays with you, but that is the concept, right? So are there any doubts on recursion before we move ahead? Was I too fast? Was I too slow? Are there any doubts? If you have, then speak up. Okay, I assume there are no doubts. Okay, so the next step. This is another topic that was covered in your.
Fine.
Yeah. Okay. Yeah.
No, just it was fine.
Yeah. Uh, I cannot hear you. Were you saying something?
Nothing. Just say it. It's fine.
Oh, cool. Okay, so let's move on. Another topic I'm pretty sure was in your lecture zero notes was complexity analysis. Um, Complexity analysis, why do we need it? So let's think about it. There can be two ways, or three ways, or even n ways of doing something, and some ways can be faster, some ways can be slowed. Uh, why do we want the fastest way? Or more importantly, how do we figure out the fastest way? As for the why, the motivation is simple. Something that takes too much time, we will not be able to compute it in a lifetime. So, for example, remember the earlier days when we used to have very slow computers. At that time, for example, the efficiency of a program used to matter. If the program runs very slow, then it will take so much time for it to load, so much time for it to run, and we'll probably lose interest by the time it actually gets to running. A lot of times, it might never get to run within a lifetime, right? So we need to be very cautious about how we are utilizing our computer resources. The same the same problem, if formulated in different ways, can actually have different time of completion. So it's important that we start seeing which code is efficient, which code is not efficient. There's always a stupid way of doing things. There's always a smart way of doing things. The stupid way is usually the one which is most intuitive, but that's not the way which we're looking for ever in life. It's always a starting point, especially for your competitive coding. It's always a starting point because then you get the idea of how to implement it. But it's never really the point we want to be. At the end of the day, we want to be the fastest and the lightest possible implementation that can happen, right? Um, so, for example, uh, there's a graph of the time that is taken based on the complexity, and I'll get into the complexity, what the notation this O thing means, but you can see that for some lines are very flat, so the time taken is not increasing as the number of elements are increasing, but for some the time increase is drastic for a very few increase in elements. We want to be on the lower side of this graph. We want to be in the orange and the blue lines, or at least worst case, we want to be where this green line is. We don't want to be in these other three lines, typically in life. So we might be able to even excuse ourselves for the red line, although it's a bit exaggerated, but yeah, we don't want to be on the steepest two lines ever. So let's see how we analyze it. Formally, there's this thing we called as the big O notation, and I never really understood why they, named it big O. Like complexity starts with a C, so sure. I mean, maybe they would have said operations or whatever. But the big O notation is essentially, and the O is essentially useless in a way. You just say O of how many steps the program takes. So, for example, and the easiest way is to get through the code. So, for example, if you look at this code, uh, one step is initializing and creating this integer. Now it depends on the language. For example, this might be two steps. So the language decides to declare it first and then initialize it. So that might be two steps. I'm considering it as one for now. Doesn't really matter in life. This is another step. So there are two steps. Then this is the third step. Okay, three steps so far. Pretty good. Then there are n steps. Okay. And what's n in this case? It's 10. But n can be anything. We are choosing it, right? Uh, and then there are two more steps. So total, we seem to be having 5 plus n steps, which is 15 in this case. But what say if you had 100 instead of 10 for the value of n? You would have 5 plus 100. Let's say if n was 1000, you would have 5 plus 1000. It would have been. So as time goes on, you realize that the value of n is more important than the other steps that take one time. So overall, we say that we always look at what the closest function is, which uh, provides the maximum term of complexity, at least for most cases. So here, n is let's say if you start calculating the number of steps, you'll say your steps are n plus 5. And n plus 5, you can say that if n is very large, it approximates to n. And that's why you write on. Let's say if there was a for loop within a for loop, and both of them had n steps. So then you would have said, okay, so n into n plus 5. So overall, you would say n square plus 5. But then you can see that as n increases, 5 is very small. So you would overall say it's on square, and so on and so forth. So that's why let's have a look at a few. Okay. Let's start to consider a few problems. So for example, if you're ever thinking about implementing something which has, let's say, 3 for loops, each of which take n steps, then you're suddenly in on cube, which is huge because 10 steps, because if the value of n is 10, your number of steps are 1000, because n cube. But then if you had an equivalent implementation, which only took O of n time, then if you could have gone for n is equal to 1000 while taking the same steps. So you can do a lot more computation if your complexity is lower. So essentially what you want is the function within this to be smaller. So, and practically, at least for competitive coding as well, you want it to be n log n at worst. Or preferably, you will try to implement an on, but on is probably not going to happen. You want to be on log n, and worst case, sometimes you might need to be n square. Not an issue. Worst case. But then again, the value of n also matters. So for example, um, if n is limited to 100, then what's n square? It's only 10,000 steps. But a computer is so fast that 10,000 steps is nothing for it. So you will not suffer anything in your test cases when you're trying to solve a problem. So it is important when we're solving problems, specifically the way that you're going to be solving for the next few months, that we not only look at the complexity. So the first job that we have is obviously to find out this function within O and find out, okay, this is the number of steps that my program, which I'm thinking of, is going to take. But the next big thing also is to know what the value of this n is. If this n is very small, if they say that that the limits are 100, then you can go to n square, you can go to n cube even, and your program will pass. It's important to have a trade-off because sometimes you cannot make a implementation very efficient as well. The nature of the problem is such that it is not very efficient. So I'm pretty sure a few of you will take up some courses in which you get to analyze different types of problems, and then you'll get to learn that there are some problems like n problems, np problems, and p problems. So for np problems, you will not be able to do it. The only way you'll be able to do it is if n is limited, and then you are iterating over multiple loops. You'll see it happen in front of you as you practice more and more. So this is something we'll discuss when we're taking over the problems in the last few sessions. Not for now, but just keep this in the back of your mind that whenever we are going through any data structure, and later on whenever we're going through any algorithm, someone's unmuted their mic, I guess. Wait, who has? Right. So whenever we're going through any data structure and later when we're going through any algorithm, make it the first point to ask what this complexity function is, right? Take a lot of practice, have a look at every code you write and try to figure out what this function is. it's very important. You need to do it for every problem, right? So now that it's done, let's actually do some data structures. So before that, just one last thing. What data structure should you choose? There are problems in which you can, there will be a lot of problems wherein you can solve something by data structure, let's say a linked list, something by, let's say, a trie, let's say a hash map. You can solve a problem using 4 or 5 different data structures. Which do you want to use? And this is a very, very common thing, and you need to learn how to differentiate. So obviously, as I said, the complexity analysis is important, but also what is important is seeing what the constraints on your inputs are so that you can see what the total value is. You don't want to do complexity analysis in an isolation. So for example, if let's say you have two functions, n and m, let's say you have two variables, n and m, n can go up to 100 and m can go up to 1000. It's equivalent if your algorithm or if your data structure is in n cube or n square. It's faster if it is in n square compared to m. So it's faster if it's in, sure, n square compared to m square, right? So not every constraint is equal. Not every data structure is equal. Not every implementation is equal, right? It is important that you calculate the total number of approximate computations you need. Um, that's one aspect of it. So that is our first point, optimal execution speed. Second is, a lot of times when we are trying to speed up our data structure implementation, a lot of time the speed up happens because we are storing a lot of data. So if you want to store, let's say, a database, then if you want to access every element in O of one time, then you'll be storing everything. And then it will take up a large storage space. But let's say if you can relax it and if you can access it in more steps, then you can store it in a much more optimal way. So sometimes you will have constraints on memory that you'll be given in your CP problem. So it's not necessary that there'll be constraints. Usually time is our limiting factor. Storage is not, but it is an important trade-off that we must remember, that storage is also sometimes a problem, as is time. And sometimes they are lenient, more lenient on time than on search. So do keep this in mind. But the last thing is actually the last thing is also equally important. If there is a data structure which is very complicated, that you will take, let's say, an hour to write, and another data structure which is less complicated and will take probably 10 minutes for you to write, if it does not matter that much to how much steps you're taking, it's probably better to go with the second one, because you'll have more time for debugging. You probably won't make as many bugs, and so you'll be able to get your answer out there fast. It's important to get the correct answer fast, but before you have the optimal algorithm, before you have the optimal speed of running your code should at least run. Running is the first condition. If it cannot run, you cannot say, oh, I implemented this fancy algorithm. Sure, you implemented a fancy algorithm, it works, but there's a bug. You've not been able to debug it because the code is so big. So no one cares. You need to get it to run. You can optimize it later. So you need to, now there are two ways of doing it. For example, you can take something very simple and then implement it. Sure. The alternative is you practice so much that you can implement tough data structures very quickly, right? So that's where practice comes in, because you need to be able to implement a complex enough data structure very fast, and so on and so forth. So it's all these three factors that you need to keep these in mind. It's not that you can only go by with one or by the other. And I mean, there's a reason why I'm probably talking a lot about this, is because I personally face this problem. A lot of times I will think of a solution which is very optimal, But then while implementing it, it is so complicated that I do end up making a lot of mistakes. And that costs me time later on. And I'm probably not able to finish it in time. It's happened a lot with me. So it's important to be able to strike a balance between these three things. I hope you'll keep this in mind when you do start your competitive coding preparation. And in your initial days, when you do start preparing, ensure that you're actually thinking of multiple approaches, not just one approach. Think of multiple approaches so that it opens your mind up. Sometimes you start seeing patterns in things that you wouldn't have seen otherwise if you were just going for that one obvious way. Like, for example, if you look at Geeks for Geeks, they have a whole hierarchy. Like, they start off with a simple solution, then a medium solution, then a complicated solution. They do it for a reason. Sometimes you only need the simple solution, sometimes you only need the hard solution, sometimes you can make do with the medium solution. You need to be able to think of all different solutions. We will discuss those, an example or two in the last two sessions, so do attend those. For now, let's start off with the data structures. The first one, and the simplest data structure, is a linked list, which is essentially one person after another, one after the other, one after another. And it just goes on and on and on, right? One after the other. So there's not much that you can think of in a linked list, but as I go on, there'll be pictures included, so you'll be able to see how it looks like. Uh, Sure, I'm pretty sure you've seen a lot of linked lists, but I'll go as I go on. I'll show you for each of the others. Um, Here you have five different linked lists, five different types of linked lists. These are the ones that you're mostly going to be concerned with, at least at this stage of our preparation, because others are a bit overkill and we don't really care for uh, complicated implementations. In fact, most of your problems can probably be solved by doubly linked lists and stacks. Maybe sometimes you need queues, but uh, circular queues, not even all the time, but most of your problems at this level can be solved here. And it's important to know that the standard library within C++ or Python or any whatever language of your choice, the standard library usually has implementations for these, but because most companies want to see your skill at implementation, they will disable it. So it is important that you know how to implement it, and you know how to implement it very fast, right? Um, okay, so let's just start off with um, singly linked list. I will also not be giving implementations for everyone. I'll be discussing the implementations. I'll be discussing the idea. I expect that you guys do some homework and that you do try to implement one. You do try to implement the others based on the one that we've seen right now, right? Otherwise, because there's no benefit that you can get if I'm telling you everything, all the benefit comes if you practice it, right? So here's a singly linked list. This is the one that I'll be discussing, the code specifically, and I'll be discussing the idea behind everyone. But the singly linked list, as you can see, is just a box followed by another box followed by another box. That's it. And this box can be as long as you want it to be. And the only thing here is that every box needs to know how to go to another box. So for example, this arrow which shows that you're going from A to B, that's the only condition we care for. And it's a singly linked list, so one box can only go to another box. So for example, A can go to B and B can go to C, but A only knows how to go to B and B only knows how to go to C. There is no connection between A and C. There is no connection between B going back to A. Every box just knows the next box in one given direction. So you cannot go in the reverse direction, and that is a problem in some implementations, but it is efficient on memory, for example. Okay. Uh, as you can see that here, the most important thing then is that we always need to keep the location of the box A stored with us, because if this location is forgotten, then we can never go to any element. Okay, sure, we might if we've forgotten A, let's say, and we remember B, then we can always go from B, C, D. Okay, sure, but we've forgotten A. That A element will never be available to us. So it's important that if we want the entire list to be available to us, we always need to remember the first element that is available to us. Now, within this element, what data you're storing, what you're doing, that's up to you. No one's going to ask you, no one wants to know what you're storing in this. It's up to the problem. But the idea behind it is to keep note of one element, and every element keeps a note of the next element. That should suffice, right? And when you're at the last element says, okay, I don't know any element, so my next element is none, null, or whatever your language says. You can even say zero, big deal. But two things that you need to know, that's all, right? So what data do you want to keep it in A? It can be a number, it can be an index, it can be a string, it can be a name. Let's say you want to store a rank list of people who scored marks. So you say first in class, second in class, third in class, fourth in class, and so on and so forth. And you store their names and the marks that they've gotten, their age, whatever you want to, and you store that one after the other. That works, right? So the data is up to you. It depends on the question at hand. So and okay, so let's make this a bit engaging. Uh, what do you think? And any one of you can answer and unmute. Whoever wants to answer, just type in the chat, I guess, because I guess you're all attendees. Uh, but whoever wants to answer this. How many steps do you think it will take to get to any element which is in the linked list? So how would you generally, what would be the number of steps in general taken? Assume any length of the linked list, and you can explain it in any way. But how many steps do you think it will take to get to any element of the linked list if you're doing this sort of a linked list? Let's give it a try. Anyone? Yeah, you can raise your hands. You'll just get unmuted, I guess. And I do want an answer from you guys. I just don't want to tell it because I want someone to answer. Assume that there are, let's say, 10 elements in the linked list. So what do you think, how many steps do you think it will take for you to get to the 8th element or to the 9th element? Or let's say 6th element, any. Would anyone like to volunteer, or can we let either of the Vanshi and Shruti nominate anyone and tell that person to answer?
There are a few answers in the chat.
Sure. Yeah. Okay. Sorry, I didn't get chat notifications. Yeah, you're right. Ashutosh, Gyandev, and Shashank, you're right. It does take n steps. And that is probably not very efficient because you're taking that many steps to go to a given element. You can access a given element in one step if you want to, if you design your data structures in a different way. We'll get to that later in the next lecture, probably. But yes, so if you want to go to any element, it will take that many number of steps. So 1 to 2 to 3. And if there are n elements, it will take you n steps. So it's not unoptimal, but it's also not very optimal, right? So what all can we do with the linked list? There are three things, basic three things. We can add elements to it, we can remove elements from it, and we can go through it. pretty much covers everything that you can do with a list, really. You can scratch off, you can add things, and so on and so forth. So let's have a look at what do we do if we want to add elements to the list, right? I don't think there's a lag, it probably seems, between. Yeah. So let's say this is our list. It has 5 elements, and this is how we're going. A is the first element. Also of note, the first element is known as the head of the linked list. So the head of the linked list it's just technical term. It's the first, it's the technical term. But as I said earlier, it's the one element that matters to us, because if we lose it, then we lose access to the entire list. We need that element, right? Let's say you want to add an element between B and C, for example. So how would you do it? Well, you first create a new element, right? And then that new element needs to be done in such a way that that new element F should say that C is next to me, and now B should say, okay, F is next to me. Because we want to add an element between B and C. It means that the order of going, or the order of traveling, should be from B to new element to C. So what we need to do is remove the connection between B and C and add a connection in such a way that B says the next is F and F says the next is C. Pretty straightforward. And you can do this between any two elements, right? And it will still maintain a list structure. Sure, it looks crooked right now, but then this is pretty straightforward. And as we've seen, the logic can be written in a pseudocode. Earlier, our situation says that next of B is C. Now what do? We create a new box. We say the next of that new box is C. And then we say that the next of P is the new box. Pretty straightforward. There's nothing more to it, right? Now, this will be different when we are discussing a doubly linked list, because there are other things we need to take care of. It will be different with a stack, with a queue, everyone. But you need to think of those on your own. For a singly linked list, this is enough. This is important. It only goes in one direction. And so that is the one direction we need to change. Now, similarly, you can remove an element from the list. So let's say you want to, there's a duplicate C. I probably should have corrected my slides, but okay. Let's say you want to remove the elements, one element between B and the second C, right? And let's say you want to jump directly from B to the second C. What do? It's pretty simple. You say that the next element to B is the next to next element to B. So the next element to B is C, is first C, and the next to next element is the one that we want. So instead of saying that next of B is this, you just say next of B is next of B. Pretty straightforward. And then, although the middle element has not been removed by any means, it is still present in memory unless you do some sort of a free operation or something. For all intents and purposes, we don't care about it because we'll never be able to get to it. The only thing that a linked list stores is the next element. And if the next does not point to that element, then that element is as good as dead to us. It's like one of those movies after you say that I'm not talking to you, you're dead to me. It's kind of like that. It's a linked list way of saying that, you kind of dead to me. So that's how you remove an element. It does not remove it from memory unless you do something about it. In competitive coding, you don't. In real life, when you're building applications, you need to do something about it. Okay, so okay, I have to edit this one. Forget this. I had to edit this one. I forgot to edit it. But essentially, the idea is that you'll say that the next of B is equal to next of B. So straightforward. What's the next thing? What's the next thing that we can do with a list? Well, we can go through it. What do we need to go through it? We only need to know one thing about a list. What is its head? And that's it, because once we know the head, every element says that every element will tell us the location of the next element. So we take a head, we assign it to a temporary variable. Now, the reason why we assign it to a temporary variable is because we'll keep changing the temporary variable. We always want the temporary box to be the box we've currently been at, and then update it to be the next box. If we do the same with head, then we forget the location of head, and we cannot afford to do that because the linked list would then only be, we'll only be able to go through the linked list once for its lifetime, and then it's useless to us. So that's why we create a copy, and then until there is a next element, you go until there's a next element, you go to the first element, you do whatever you want with the data. You can print it or change values, whatever, and then just make the temporary element the next element. And then you repeat it. And this keeps going on and on and on until you reach the end of the list, at which point the next does not exist. Then it stops. So this is how you go through a linked list element, a linked list, right? Um, how have you seen it in reality? You've probably seen it as an array. An array is essentially a linked list. Um, you have a fixed number of elements, one after the other. And I mean, sure, an array is similar in a way. It's not exactly as dynamic or as flexible as a linked list, but then this is how you can think of that an array is a fixed set of n elements, one after the other. In array, you can access every element at one time, but sure, if you let's say add any element at the end of an array, you'll need to first go through the array to find out, okay, this is the place where the last element was added. This is the array which has, this is the size of the filled up array. So let's say an array has 10 elements and you add one element one by one. Default value, let's say, is -1 for everything. So you iterate over the array, you find out where the first element is, which has a value of -1. You add a new element, and then you can do that similarly for adding. So this is similar to how you do for a linked list. Similarly, if you want to remove an element, you go through the array till the end. Wherever you find the first match, you shift every element to the right of it back one step back. This is similar to how you do with the linked list. And you can also go through an array, in which case you just iterate from the starting index to the place where the value is -1, and you print the value or you do whatever you want with it. So an array is kind of an implementation of a linked list, but it's not very flexible, because the beauty of linked lists is that the size of the linked list is not fixed. And array, you need to know your size at the compile time. It's fixed, so it loses all benefits that you would get from a linked list. A better implementation of your linked list is a dynamic implementation. And in a dynamic implementation, what you do is you create objects, So, okay, objects. I'm not sure how many of you have done object-oriented programming, but okay. A dynamic implementation essentially means that your memory is allocated dynamically, which means whenever you need it, you take more memory and you allocate it. A static implementation is that you give the memory once and then you use from that memory. The problem with static is that you don't know how much memory you'll need beforehand. The benefit of dynamic is that you can take memory as you go along. The important thing is that if you take any memory, once you stop using a memory element, you need to free it. Otherwise, there will be a situation where you'll be wasting memory that you're no longer using. And this is a problem. But it's not relevant for us right now. So anyway, I'm pretty sure you're aware of structs. A dynamic implementation of linked list would essentially just create a struct, name it whatever you want to. I'll name it node, whatever. This has an int data element in it. You can store anything, any number of things. It can be 10 data elements, it doesn't matter. The only thing that matters to us is that it points to a next node. So this statement is essential. And at the end of it, if we want to access a linked list, a Syncly linked list, we need to know its head. So apart from these two things, we really don't need to know anything. And this is the crux of what a linked list is, right? You can have um, all the behavior that I described earlier. You can implement them in functions like this. You can go through this, for example. And so as I said, let's say if you want to add an element. So let's say you want to add an element at the head. Now, this can be done at any point. You can say, let's add an element at the end of the list. So you will first you'll go from the head to the last element, then you'll create a new element and point to it from the previous element. Works. You can add to its head. You can add midway based on a value. It's all in your hands. But the logic is that you need to update the next of one or more elements involved. And you need to ensure that you store head, right? Because if you don't store head, then you lose your linked list. That's the only crux that we care about. The implementation will be problem specific. Similarly for remove element, let's say you go to some point where you, let's say, so here you're traversing until you get to the end. You go to a point where there is, let's say you want to delete 5. So let's say you want to delete the node which has a value of 5. So you run to the node which has a value of 5. You find it, okay, this is 1. So then we'll delete it. How do we delete it? Well, if there is a next to next, then the next should be the next to next. We skip the next. If there is not, then the list is gone because the next would have been the last element. So you don't need to care about it. So the next is removed and the current element becomes the last. This is how you would do it, how you would remove an element from linked list. Similarly, this is how you would go through a linked list. You keep a copy of the head, keep going until you reach the last, do something with the data, and then update the copy to go to the next, and so on and so forth. You'll go until you reach the end. This pretty much covers the single linked list. And so if you have any questions, let me know in the chat right now, or just ask yourself to be unmuted so that we can discuss. Any question? Does anyone have any questions? Okay. So can I assume that there are no questions? Okay. I was hoping for some questions actually because it gets boring if I keep speaking and if only I'm speaking, koi aur bol raha ho, to it becomes interesting. So I hope if you have any questions, please. Anything. Okay, so I'll assume that there are no questions. Let's move on. So, stay active, please. Whatever you have in mind, just say it on the chat. Like whatever questions you have, nothing else. Okay, so doubly linked list. What's so special about this? Well, a single linked list, we knew the first element, and every element knew about its next element. In a doubly linked list, every element needs to know about its next element and its previous element. And for convenience, we also keep a track of the last element so that we can go from both directions. So from the first element to the last, or from the last to the first, we can go in both directions. Or at any point, even in the middle, you can go between. So for example, if you're let's say somewhere in the middle of the linked list, you can go you can go towards the front or you can go towards the end. So that's the only difference between a doubly linked list. So now let's say you want to add an element. What do you do if you want to add an element? Well, how would you add an element? Between two elements, if you're adding a third, then you need to ensure that the next of the first element points to the new element and the previous of the third element points to the new element. But that is not enough. The new element should also be should also have its pointing of next and previous in such a way that the new elements next should be pointing to the third and previous should be pointing to the first. You need to update your now because you have 2 pointers, you also have double the responsibility. You have to ensure that all the things are pointing correctly. Otherwise, if there's any break, then you will have bugs in your code. So ensure that your next and previous of all the elements that are affected are being updated correctly, right? Beyond that, everything else is similar in a doubly linked list. Also, if you can think about it, uh, how much time do you think it will take for you to find an element in a doubly linked list? In a single linked list, it will take you n steps. How much time do you think it will take for you to do so in a doubly linked list? I would like an answer. Any one of you can answer. And more importantly, is it faster to find something in a doubly linked list? Okay, so Shashank says it's the same. In terms of the overall function, I agree that it is the same. But if you're very concerned with the specifics, then I would say it takes half the time. Because if you're wanting to find someone, if you want to find some element, you can now traverse from both the first and the last in the same time. So your loop runs half the number of times. But obviously there are twice the number of statements, so it compensates. But your iterations happen for half the time basically. And within the loop, if let's say you had 10 statements, now you'll have 11. And so you can see a benefit there. If you're if the processing that you do after finding is a bit more complicated, it can be faster if you're using a doubly linked list. But again, it will take twice the storage because every element is now storing 2 pointers instead of one. And a pointer will take as much space as, well, it depends on the uh, architecture of the OS that you're running on. But if it's a 64-bit OS, for example, a pointer will be pointing to will take a 64-bit size. So pointers are costly. Int, for example, takes 4 bytes, 32 bits. Pointer will take 8 bytes. So be careful because you might run into memory problems, especially if you need a linked list of, let's say, a million elements, because a million elements means a million elements into the size. So let's say 8 bytes, 8 bytes, 4 bytes, 20 bytes per element, and million elements, which is 20 MBs. It's possible you might run out of memory, right? So you need a few tricks at times. Also, it's possible to have a dynamic implementation in a static way. So I'll get into that once we're actually in the problem discussions sessions, but you can have a dynamic implementation using a static memory allocation. And that is very useful in certain cases. And in certain tough questions by certain companies, you will need to do that. It is very important to do it that way. Other methods will not work. Malloc, new, it won't work. Okay, stacks. The coolest of all the linked lists. Uh, I'd say it's the coolest. I think it's the coolest because it seems to represent a lot of reality in it. So, what's a stack? Well, it's like an arrangement of things in your room, or let's say an arrangement of hula hoops on top of the other. Like you place the first hoop down, then you place the second hoop down, and the third, and everything is placed on top of the lower one. And when you want to remove, you just take the topmost element, and then the next top, and then the next top, and so on and so forth. It's similar to how we keep at least I keep my clothes in my room. Like you put everything down, and then whatever I want to wear, I'll just take the top one. You know. So this type, you can think about how the data is going, and you can say that this is a last in, first out, or a first in, last out arrangement, because the first element goes to the bottom, and the last element is at the top. You're removing from the top, so the last actually comes out for the first. I want you guys to try implementing this using a linked list and Also by using an array. Array is the easier way out. Usually I would prefer array unless the problem requires a lot of size, which point you can go for linked list, but try implementing stacks. They're very easy to implement. And the only thing, yeah, also I forgot to see Shashank's message. Yeah, you're right, Shashank, that if we have the more the number of pointers we have, the faster we can access any of these list structures. The more pointers we have, the faster we can actually go. Um, but but then again, it's always a trade-off between storage space and time complexity. So you're saving marginal amounts of time at this point. If you go beyond 2 pointers, you're saving marginal amounts of time, but you're gaining a lot in storage. Like every additional element is a significant percent increase. So if you go from 2 to 3, you're getting a 33% memory increase. You are getting a slightly lesser than 30% time increase decrease, and you can actually, yeah, you're still working in O of n. So you're just doing O of n by some constant, which is still O of n. So it can be faster, but memory becomes more important at a given point. Um, right. So how would you want to implement stacks? Well, stacks is to two things. You want to add something to the stack, or you want to remove something from the stack. So how do you add something to the stack? Well, uh, you can do it in a singly linked list. You can do it in a doubly linked list. Let's go with a singly linked list, for example. So implementing a stack would be that every last element, that every new element is the new head, for example. So you create a new element. You say that the next element of this new, the next of this new element is the head of the linked list. And then you just say that the head of the linked list is the new element. That's it. So now that you're going to the, so now that when you're traversing this linked list, the head will be taken at the last. The first element will be done at the last. The last element will be taken at the first. That's how you would implement a stack in a linked list. In an array, it's even easier. Like you add it towards the end and you start traversing the array from the start. That's how a stack would work. Similarly, if you want to remove an element, just do the reverse thing. So earlier we were adding to the head and updating the head. Now you take the head, remove it, and make the new element the head. So you just take the first element out, go to its next element, make that as the new head. That's it. Um, anyone has any questions in stacks though, or anything up till now? If anyone has any questions, uh, type in the chat, and Divyanshi and Shruti, if you can unmute them, it would be nice to have any audio questions. Okay. No one seems to be having a question. Okay. Stacks are cool then. Let's go to queues and let's get to some nostalgia in that case. Um, Shiru Cafe. I hope none of you here are freshers because it will be a bit painful agar you're getting to see the Insta for the first time and it's in a slide. Will be data structures ka at night. That would be very kind of sad. But for the rest of you, I know we all miss Shiru Cafe. It's cool. And we've all seen these huge lines in Shiru Cafe, like everyone after 10:30 class, 8:30 class, 9:30 class, every morning class, everyone just wants coffee. And the lines, like, they extend from the counter to the Elec'20 area, and everyone's just standing, oh, we want coffee, and someone's friends will get in their way and everything. So um, this was actually all these people I are actually from my batch. This is a photo from my time, and we were given like free t-shirts and everything. So Shiru Cafe has this thing once every year in which you get a free t-shirt. So only the first few people do, first 1,000 people or so. So you see massive lines. But that's the idea behind a queue. So you stand one after the other. the first person gets this coffee and leaves. The next person comes, next person gets coffee and leaves. And I know coffee is not necessary, but let's just get to it. Um, if- but think about it. If this was done like a stack, then no one would have any incentive to actually stand and wait in the first line because a stack is last and first out. So if your lines at Shiru Cafe were like a stack, you would actually get rewarded for being the last person to come to Shiru Cafe, which would be so unfair, right? So that's why some things are best as queues, some things are best as stacks. Uh, yeah. And how would you implement a queue? Well, you just remove you just open up the second gate. So you add something on top of another, but the thing at the bottom gets removed first now. So this is most naturally implemented using a doubly linked list. So yeah, so let's say you add something at the tail and you take something out of the head. So a queue is most efficiently, the representation of queue is most natural if you're doing it through a doubly linked list. The representation of a stack is most natural if you're doing it in a singly linked list. And the representation is here. So for example, you add any element to the tail. So you create a new element, let the tail point to it, and then update the tail. And when you want to remove an element, you take the head out, and the head's next element is now the new head. That's it. Uh, yeah, yeah, Ashutosh, so sorry for that. I just felt very nostalgic about the instinct. I love Shiru Cafe. The people there were very interesting, and you could always see someone who was doing some sort of design and drawing, and some people would be chatting up. Uh, a few of the people at Shiru Cafe, they were very friendly also, so you'd be having photo sessions with them. It was very cool. I hope the college opens up soon though, because I really want to visit it once at least. Yeah. Okay. Does anyone have any questions, thoughts, doubts, anything even related to Shiru Cafe, whatever? Please raise your hand and let's take a 5 minutes breather. So please raise your hands and um, you'll get unmuted. Speak it out, whatever you want to. Um, Let me know if my pace is too fast, if it's too boring. Let me know what I can do better. I'll be better prepared for the next session. So anything you want to say, just raise your hand. Um, and everyone else just take a 5 minutes breather. And how about you make some coffee? I'm really tempted to play some music right now, but I would not. So please raise your hand, someone. Okay. See, breathers का कोई point नहीं है if I'm the only one talking. Someone needs to speak up. Shruti, any doubts from your side? Or anything, basically? Um, Ashutosh has no questions. Okay. ठीक है. Every one of you is smart here. I'm pretty sure a lot of people have studied. ठीक है. Let's go on with trees then. Yeah, so where did the idea of a tree come from? Well, it came from a tree. Spoiler, spoiler. Like, that's how trees are generated. You have one root and then the tree just expands. And I'm pretty sure someone got lost in the desert. They had some quote unquote cookies and they got high and then they started saying, oh, let's make this into something. We'll commercialize it. We'll call it a data structure and we'll get famous all over the world. And students all over the globe have to study it. So I'm pretty sure that's how it happened because this image is like too much of a coincidence. Like, are there aliens between us? I don't know. Among us, I don't know. Uh, but sure, that's the idea behind a tree. Uh, a tree, like a natural tree, you start off from a root, it grows up, it has branches, Every branch has more branches and more branches and more branches. And at the end, you have leaves. And that's it. That's where the tree ends. Similarly, that's how a tree data structure is created. You have a root, a node, which has nothing before it. And this is the first element, and everything comes after it. And then you have that root giving has some children branches, and then those children have some more and some more and some more. And at the end, there are another few elements which only have parents, no children. So a root element is one which has only children, no parents. A leaf at the end is is a node which has no children, only parents. And for a given general tree, um, there is no fixed number of children that any node can have. So it's not necessary that uh, there is a fixed number of branches that can emerge at any point, just like in a general tree. Some branches have 10 branches, some branches have 10 sub branches, and some branches have no branches at all. They just end at a leaf. So there's no limitation. But then implementing this becomes very tricky if you don't have any constraints on the number of branches. You need to store it using a variable number of pointers. Why would you want to do that? So in that case, we have something which we call a binary tree, in which case uh, you have a tree such that every node can have at most two children. So they can have a left, or they can have a right, or they can have a left and right. They cannot have a left, right, mid. So they can only have two. They have one, they can have zero. They can have zero if they're leaf, but they can have one or they can have two. Uh, there are also tertiary trees, in which case every node can have up to three elements. You can have quaternary, you can have n-ary in general. But in life, most implementations in CP you can do with a binary tree. You don't really need to go beyond two children per node, right? So here essentially like so what's exactly the difference between linked list? A linked list is in a sequence. It goes one after the other. So at any given node, either keeps track of its next or of its previous. But a tree keeps track of its previous and multiple nexts. So that one next ki jagah, there are multiple nexts. That's the crux of the difference between a tree. And if you look at any one path within a tree, it is essentially like a linked list, right? Let's say if you look at HGDC, HGDC, and if you cut everything else, it's essentially a linked list. So a tree is a more general data structure than a linked list. In fact, you'll see this as we go through more slides, is that you always move towards I'll always try and move towards more general data structures. So linked list was the most specific and the simplest. Tree is a slightly bit more complicated and a bit more generic. Next, we'll go to graphs after this, not today, which are even less generic, which are even more generic and even tougher to implement. Okay, so this is binary tree. um, right. So as I said, how would you implement it? Now I've decided to uh, let it be one-way traversable in the sense that you need to go from root to the leaves and you can never go back up. But then this is your choice. I mean, here I'll need to ensure that my root is never forgotten, and that's it. But you can have a pointer to the pointer that says node star parent. You can keep track of your parent also. That's up to you. There is nothing like a doubly linked tree or a singly linked tree here. In general, trees can be however you want them to be, but this is the concept that you have. How would you add an element? Well, you just go to some node and you add it either to its left or to its right. But where do you want to add it is something that you can think of. So in general, you can add it anywhere, but if you have some logic, you can make your life simpler. So let's say there's a thing called as a binary search tree in which you add in a certain way. There is a heap in which you add in a certain way. So you can add with a certain logic to make your implementations faster and smarter. And trees, for example, when you're going through linked lists, we could use a recursion to traverse through them, or we could use an iteration. With trees also, we can do the same, but it is much easier if we use recursion in trees, because with iteration, we'll need to start thinking of all conditions. So first you iterate to left, and then you think, okay, we go to left and then right. But then if you go to this left, then we go to left and right, and then it can become complicated if you're not implementing it correctly. Whereas implementing it using a recursion strategy is a two-liner type of implementation. You'll see those implementations within the booklet. That's why I've not put them in the slides to keep the slides short. But that's what. At the end of the day, a tree just contains a binary tree. This contains a pointer to a left element and a right element. These left and right elements are also trees, so they're called subtrees. So you have a left subtree, a right subtree. And for every node within the tree, you keep a value, or you can keep a set of values. So it can be anything. Again, the data that you keep in a tree data structure is totally up to you, depending on the problem, right? So how would you go through a tree, a binary tree? Uh, shouldn't have revealed the spoiler before shouldn't have revealed the movie before the trailer, but then I wanted to ask you, how would you go through it? But then there are different ways of going through it. See, a linked list does not have any degrees of freedom. It's just one after the other. So going through a linked list is very easy. You just go to a current element, go to its next, then to its next, then to its next, then to its next, and so on and so forth. But with a tree, you can go, okay, first I want to go to the element, then I go to its left, then I go to its right. But you can say that, oh, first I'll go all the way left, then I'll go one step above, then I'll go right, then I'll go above, then I'll go above, and so on and so forth. So three ways of going about it. First is an in order way. And how do you remember this? Is like in order is left, self, right. Pre-order is self, left, right. And post-order is left, right, self. Right? No one's going to ask you though about how you're going to traverse it. I mean, they might in an interview, obviously not in an implementation-based competitive coding, not in a coding round, but in an interview, sure, they might ask you. So it's important that you know how you traverse. So let's have a look at the in order. In order says left, then self, then right. So I start with 1. Then I first go to left. Left of 1 is 2. Then I go to left of 2, which is what? 4. Now 4 is where I ended. There is no left of 4. So now I go to self. Self of 4 prints out 4. There is no right of 4, so I go up. Now I go to self of 2, which is 2. So it prints 2. Then I go to right of 2, which is 5. Now this is done, so I go one step up. Now I print self of 1, which is 1. Then I go to right of 1. Right of 1 is 3. But then it has a left, so we first go to left, right? And yeah, they've printed wrong. So we go to left here. So left first we print 6. So this should have been 6. I don't know what they've done. Now this one does not have any left or right. So it goes to left, doesn't find anything. Print self, goes to right, there's no right, goes up. Print self, so 3, then goes right, print 7. So the order should be 4, 2, 5, 1, 6, 3, 7. This is a misprint, so ignore it, but you should know the logic behind it. Similarly, you can have a pre-order, which is first you go to your self, then you go to left, then you go to right. So you go to self, you start with 1, okay. Then I go to left, which is this. First I process self, so I print 2. Then I go to left, which is 4. Now I first process self, which is 4. Then I go to its left, nothing. Then I go to its right, nothing. So I go back up. Then iska self the self of 2 has been completed. The left of 2 has been completed. So now we go to right of 2, which is 5. Prints the self, so it's 5. Goes to left, no, nothing in the left. Goes to right, nothing in the right. Now it goes to goes one step up, 2 is completed, now it goes to 1, the self of 1 is completed, the left of 1 is completed, so it goes to right of 1, it goes to 3, prints 3, self of 3 is completed, next it goes to left of 3, so left of 3 is 6, for 6 it will first print the self of 6, which is 6, tries to go to left of 6, which is nothing, right of 6, which is nothing, 6 is completed, goes up, now self of 3 was completed earlier, left of 6 is completed, and it will go to right of 3 and print 7 first, then tries to go to self of 7, nothing, and right of 7, nothing. So this is the order again. Go to 1, 2, 4, 5, 3, 6, 7. Similarly, post order, you first go to left, then right, then self. So first you go left, then you go left, and nothing left here, then nothing right here, then self. So 4. Then here, then 4 is completed, you move up, you go right, so this says 5, right is completed, then self, 2, then you go to 1, the right of 1, so first you go left, you've gone to left of 1, left of 1 is completed, now it's time to go to right of 1. Go right of 1, you get this whole tree, then you go to left of 3, which is 6, there's nothing to its left or to its right, so its self gets printed, so 6, then you go up to 3 and you go to the right of 3. 7, there is no left of 7, no right of 7, so you print self of 7, go up, print self of 3, and then you print 1. So this is what you would get as an order. Just remember how you go about it. Do not make mistakes. There is a very consistent order that you have to go to. Follow that policy for every node. Okay. Does anyone have any questions in this? Because this can be a bit complicated. Okay. Doesn't seem like there are any questions. Okay, so I'll move on. A variant on binary trees is a binary search tree. And in a binary search tree, we just have a condition that the values that we store within the nodes of a tree are such that the value at the left node is smaller than the value at the parent, and that is smaller than the value at the right. Now, you would have been thinking, I said earlier that you can keep anything as a value of a tree. You can keep 10 elements, 15 elements. So how do I decide which element to be kept as the value to be decided for this smaller condition? You need a number at the end of the day, right? So for this, you can actually choose whichever value you want to create a binary search tree for. We'll do this when we are discussing questions, but the idea behind putting any value in a search tree or in a heap for a more general situation is that you want to access that value in a quick time. So for example, if this was representing an array or something, and if you wanted to get to, let's say, element number 12, if you want to get to a value of 12, you know, okay, 25, 12 smaller, go to left, 20, 12 smaller, go to left, 10, 12 small, 12 bigger, go to right. How many steps did you take? 4. How many elements are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You have 16, 17 steps, however. It took you only 4 steps, right? If it was, so this can also be taken as a way of sorting. Binary search trees can also be some sort of a sorted data structure. And the benefit is that the maximum number of steps you'll need to take, assuming that every node has 2 children, which I think you fix when you're doing a binary search tree, is how many levels can you have? So if you have 1 element, you have 1 level. If you have 3 elements, you have 2 levels. If you have 4 to 7 elements, you have 3 levels, and so on and so forth. So the number of elements that you have in the number of elements you have, let's say they are n. So the depth that you have for a binary search tree will be log of that n base 2. Which means that if you're searching for anything within a binary search tree, you will take a log n time to save it, to search it. Compare that to unsorted array, and which takes n steps, This one takes log n steps, and log n is much faster than n. So this is a very efficient method of searching through elements. Similarly, you can also make the same argument for heap. This is a bit more ordered than heap, actually. So that is why we create a binary search tree. The search is within the name, and because we're trying to optimize it. So it's a log n complexity, which is a much faster complexity than n. Let's say you had 10,000 elements, or let's say if I had 1,000 elements, O of n means 1,000 steps, but log of 1,000 base 2 means 10 steps. Significant time savings. So wherever you have large values of any variable and you want to search something, if there is some sort of a data storage involved, some sort of a sorting involved, you should think towards an ordered tree structure representation. You should think towards heaps. You should think towards binary search trees. I have not discussed heaps currently because I want to discuss them later on. Yeah, because I want to discuss heaps later on. So I will be ending this lectures at binary search trees itself. Heaps will be for the next time. But whenever you're thinking of searching, sorting, or anything, a very nice and easy way is if you think in terms of trees. Now, adding an element to a tree will also take log n steps. In this case, let's say you want to add, I don't know, 7. Okay. So say we start at 25, we want 7. 7 is smaller than 25, go to left. 7 is smaller than 20, go to left. 10. 7 is smaller than 10, go to left. 5. 7 is larger than 5, so you go right. 7 is smaller than 8, so you add to the left. How many steps will it take? 1, 2, 3, 4, 5, 6. Yeah, and this has, I think, how many elements? This has, I'm assuming this has X number of elements. I don't know, but it's taking 6 steps, which is very small compared to if you had to sort an array and then add to it. Or even if you had a sorted array, you still would have to traverse until that element because you don't know how many elements you have before the element that you want to add. So adding in a binary search tree takes log n number of steps. Searching in a binary search tree takes a log n number of steps. And because you're deleting something, and because if you can, and if you, let's say if you want to delete something, because you can get to that element in log n steps, you can also delete it in log n steps, right? So this becomes a very efficient way of data storage. The problem is it might take a bit more memory if you're doing static allocation, because if you're doing static allocation, you'll need to allocate for every child's left and right. But if you're doing dynamic allocation, the memory is also efficient because it only stores as many elements as there are children. And the access time is also very fast. There is also one condition though, because if we keep adding in the way that I told you, it is possible that the tree will start having such a structure that every node will only have one child. But we don't want that. We want every node to try and have uh, two childs, two children. So if I had added 7 here, then 8 would have one child, and this 12 is having one child, and this 30 is having one child, and so on and so forth. So it'll make, as the number of inputs increase, it's possible that we might get a tree where not a lot of elements have 2 children. And in such a situation, your log n complexity will start increasing towards n, which is not a good thing. So for that, you can, whenever you're adding an element or removing an element, it is possible that you might need to do some sort of an operation to rearrange the elements of the tree such that you regain your um, structuring. Now that can be done howsoever you want to, but yeah. So with that, I'll end for today. I hope that everything has been clear, but any questions you have, just ask. The mics are allowed to be unmuted. And if you have any questions in general about complexity analysis or whatever, still ask anything. Anyone? Any questions really? Or is it everything is clear? Like if everything is clear, then awesome. But Tabibi, still ask something if you wanna. Nothing? So should we wrap up? Yeah, Mira, you can just directly ask on the mic. It's better. Everyone also gets to. No. But okay. So she asked a question: which way out of the three? Yeah, please ask. Yeah.
Yeah, so in the binary tree, we saw that there are three ways to traverse for the elements. And so, which of these ways should we use? Is that depending on the problem we are trying to solve?
So usually the problem will specify what type of traversal they want because the way of access will differ. But see, the time complexity of each is similar. So if you are doing a tree implementation and if you have complete freedom about what you want to get, then you can choose anything really. No one cares if you're using in order, pre-order, or post-order. If they want specifically, then you should just know that these traversal methods exist. Also, I mean,
Okay, thanks.
if you arrange your data in a given way, then let's say if you're thinking about going to a binary search tree, and let's say if you put in some more constraints, then you might say that, okay, pre-order is more beneficial than uh, post-order and so on and so forth. So for example, if you do, let's say, pre-order traverse, let's say if you do, uh, wait, let's say if you do an in-order traversal of a binary search tree, we first go left, 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 you go to 1, you go to self, 5, then you go to right, 8, then you go to self, 10. So 1, 5, 8, 10, 12, 15, uh, 20, 22, 25, uh, 28, 30, 36, 38, 40, 28, 30, 36, 38, uh, 40, 45, 48, 50. So if you see, if you do an in-order traversal of a binary search tree, you can actually get the sorted array. So it is more beneficial to use an in-order traversal than a pre-order or post-order, which would not give you the sorted array back. So if you add elements in a binary search tree and then you do an in-order traversal, you can get a sorted array back. So depending on what technique you use to add elements to a binary search tree, you can use a given traversal method to get to the sorted array, which is a faster way of doing it than any other method. So like this is how you would decide which type of traversal you want to do. So it's a good question actually. Does anyone have any other questions? Or was the content like too little to ask questions like? Okay. Does anyone here see a problem with recursion? In the sense that not that you have a problem with implementing it, but do you see a problem with recursion in general? Like, can the complexity go too high? Can it take too many steps? Do you see any problems, potential problems? If you do, then just speak up, because that will actually help us go towards dynamic programming when we are going to algorithms. So, does anyone see any problems? Okay. Anyone would like to have a go at it? Anyone would like to try? Shashank, you wanna give it a shot? Yeah, you can just speak up, Shashank. You can just speak up. You can unmute your mic and speak up. It's good to have a discussion.
Hello, am I audible?
Yeah, you're audible.
Yeah, so the thing is that we keep on adding, we keep on calling more and more functions. So there can be a limit to like how many times a function can be called. And that
Yeah.
in a way it limits the potential power of recursion.
Yeah, a lot of problems have a lot of problems have this, that you can only call a function n number of times, but also that if you try to do a few problems using recursion, then you actually get an exponentially increasing number of steps also. Like in a way
Yeah,
that,
like the Fibonacci.
yeah, exactly. Because every recursive function call will call more and more. So if a recursive function is calling itself more than once, then you can see that it will be exponentially increasing with time. So one is calling two, then each of those will call two, and the number of function calls that will be present on the stack will actually grow as the power of uh, as an exponential function, and this will become very inefficient. Also inefficient because for a lot of cases we'll be recomputing the values. So if you can save some of those values and refer back to them, then you can eliminate a lot of these function calls and reduce the complexity from k to the power of n to n square or kn, which is very helpful and which is the motivation behind dynamic programming also. So good observation, Shashank. Right. Because there's so few of you here, does anyone have anything or any doubts beyond what was covered today? Like, do you have doubts in any algorithms or data structures that were not covered today? You can still ask if you want to. Okay. It seems like you guys are smart enough, so we'll wrap this up then. Okay, so thanks for attending. Good night, I guess, everyone. And I'm sure most of you are not going to sleep right now because, let's be honest, no one sleeps in college at the night, the day everyone sleeps. Make yourself a cup of coffee, see some Shiruki photos, and see you in the next session. Okay. Let's Shruti, let's end this. Divyanshi, Shruti, and you.
Yes,